Right, so this is the second part of this little tutorial on statics with wrenches. So we just discussed a two-link mechanism in the first part. Now we'll upgrade to the venerable four-bar mechanism, where we added a third link. Right, so we had A and then we had B, but here I'll name them differently. A and B are two links that are connected to the stationary frame, and then C is the body link. And if we apply the same wrench recipe, which again is introduce an unknown for each joint, so we have wrench for joint 1 expressed in frame A, so it acts on link A, and is expressed in frame A. Joint 2 is this one, and the green arrow indicates that we express it in C, so we write F2C. Then we have our third joint, which acts on B, and our fourth joint, which again acts on C. Okay, so this is a parallel mechanism, but our recipe will solve that no problem. Okay. Again, we'll just eyeball the coordinate frames here. So you know, the ones that I introduced in this case is I chose to put the link frames coincident with the joints for A and B. Okay, but for C I'll put it in the middle. And the reason I do that is because I'm going to assume that there is no gravity acting on A and B, that they're just massless, right? But for C we need gravity, so I'll put it at a sort of COM in the center. But for A and B I can choose the joint frames here, so they're very simple to compute with. So maybe this is the little creativity that you need, but then again, it really doesn't matter. You can choose any link frame. So adding this to this dictionary, now we have a bunch of entries in this dictionary because we also add the inverses. Right, so I proceeded to add all four link joint frames, even though for the unknowns we only need 1 and 3, but that's okay. I might need them later. All right, so if we assume that the legs are massless, right, then that means that they will just transmit the wrench from the body to the stationary frame, or vice versa. And this is easy to see, right? If we put the wrench equation for each leg of this four-bar mechanism, we have one in A, we have one in B, then we can symbolically eliminate immediately the wrench in A and the wrench in B. For those two joints 1 and 3, as being the inverse, right? So the equation here as the reaction force, there is a negative sign, but if we bring that to the other side, we see that the wrench on A is just going to be the wrench at joint 2. Okay, so I'm just moving a little bit to show that here. This wrench here, F2C, will simply show up here in link 1, just transforming it from the C frame to the A frame. So a leg that has no mass is simply transmitting the wrench from joint to joint. And it doesn't matter actually how many joints are in between. In the end, you can actually, by the way, skip it and go straight from C to this joint, even if there are like a gazillion joints in between. Because each one will simply transmit, and these adjoints will compose. We'll see that later in an example. Cool, so the same happens here. FC4 is just transmitted to FB3, and so this is just a coordinate frame conversion with adjoint. Okie doke, well, that means that there is really only one equation left, right? Which is the equation in the body frame, because the other ones we solved already, and that cancels the gravity in the body frame. And here something interesting happens. Okay, so let's count the number of unknowns, which we have 3 for joint 2 and 3 for joint 4. And then, the gravity wrench is known, so that doesn't introduce any unknowns. So we have 6 unknowns, seemingly, and only 3 equations, because this is a 3-dimensional linear system, right? So we have an underdetermined system. This is we cannot solve this without additional information. So the additional information we can resolve in many, many different ways. So for example, one way to get an exactly well-determined system is to say that all the joints are unactuated, meaning we impose that the torque delivered by those joints are unactuated except one. All right, that adds 3 equations, and then we can choose any joint to deliver the torque on that mechanism to keep it upright. So that's one way to do it. That gives us 3 additional equations. Another one is saying, well, let's put 4 motors there, but let's minimize the torque so that now we choose out of all possible linear combinations of wrenches that keep this 4-bar mechanism upright. We choose the one that makes, does the least amount of work, right? So that's one solution. And then anything in between, really. Okay, so what we can do is we can say, let's, and this is like an animal, let's assume that the joints at the feet cannot deliver torque. In the case of point feet, that would be correct. So we have 2 equations for the ankle torques being 0, and then the hip torques will just make the minimum torque. So we have 2 linear constraints and then 2 degrees of freedom of minimization, and that solves it. So how do we solve for that? Well, now it becomes a bit more complicated, right? Now we have an optimization problem. We need to find the torques that minimize the sum of squared error, the sum of squared of the torques, subject to some linear constraints. There's many different ways to solve these, and we're going to do that here with GTSAM, right? So we're going to minimize the torque with GTSAM. So, and we'll do the hip solution. We'll say, we'll create 2 constraints on torque 1 and torque 3 that are 0. And note that this is the same as before. We just take the screw axis. Note that the torque, the wrench is just transmitted from the C frame to the joint. So the torque is just the axis that transforms from the C frame to the joint frame 2. Or joint frame 1 and joint frame 3. And we multiply that with these unknown wrenches, and that will allow us to write the constraints. Here is the factor graph that we're going to create. Actually, let me just first calculate all the axes that we need, which is a quick calculation. And here's the factor graph. All right, so there is 2 unknowns, wrench on. Remember where 2 and 4 are, so I'm just going to scroll up a little bit and show you that we have. This is joint 2 and this is joint 4, and here are 2 unknowns. Okay? And we're going to have a balance equation and then some constraints on the torques that result from these 2 unknowns. Alright, so how does that work? Here's the entire factor graph. The 2 variables are the unknowns. We have 3 degrees of freedom here and 3 degrees of freedom here, so there are 6 scalar unknowns. But in GTSAM, we typically work with multivariate quantities. So we will just introduce a variable for the wrench and another variable for the second wrench. And to indicate a linear constraint, we introduce a factor. And this blue factor is the balance, right? So the gravity wrench here is a parameter, so it doesn't show up as an unknown. It just says these better be balanced with gravity. Then we're going to say, well, we're calculating the torque here in green says this is a calculation of torque 1, which is the foot on the left, and we say that it's equal to 0, so that's another factor. And we do the same at the other side. And then we calculate torque 2 and torque 4, again by multiplying with the appropriate axes. And we minimize the sum of squares, and those are some square factors. So this is actually the bread and butter of GTSAM, is solving. Actually, GTSAM does nonlinear least squares really well, or any other noise model. But we're just going to use the linear subpart, which is really the core of GTSAM, is solving linear equations. Not linear equations, but linear least squares problems, possibly subject to linear equations. Okay, this is called a quadratic program, but with only equalities at the moment. We will not do inequalities in this notebook, but when you introduce friction, inequalities show up, and we will have full quadratic programs. So how do you do this in GTSAM? Well, we're introducing two keys, F2 and F4, for these two unknowns. Add some noise models, AL3 and AL1 is just saying that we have linear constraints. And we'll use a unit standard deviation noise model for the minimization of the torques. And then here is the whole factor graph that gets added. So we create a new empty, what's called a Gaussian factor graph, because all the noise models that we use are Gaussian. We add the two minimization factors. We add the force balance equation in the body, the wrench balance, I should say. And then we say that the torque in the feeder is 0, and this is the entire factor graph. We added 1, 2, 3, 4, 5 factors, and let's compare that with the drawing. We actually added in this order: 1, 2, 3, and 4, and 5. Okay? And we give it to GTSAM, and this is a convex problem. So let's first evaluate this cell. All right, so now the graph is created, and you can inspect this this graph if you want. So I can show you the graph just by printing it out. There's 5 factors, and here are all these 5 factors. So it's a pretty simple graph. Unfortunately, we don't have great drawing of graphs yet. But this is a convex program, so we don't need an initial estimate, as in, say, nonlinear solving. So let's evaluate it and print the result. Okay. It's not printing. Let's see here. I didn't. It wasn't in the right cell, probably. So here is the result. So we get an error of 0.06. And the wrenches are, we have some apparently, the solution to this system has some horizontal reaction forces that cancel, because they have to cancel in the body. In this case, we are getting some vertical forces that add up to 10 newtons, and we get some torques in the C-frame, okay? And that is because we created, right? So it all depends on what you choose here for the coordinates of the center of mass. And here I chose the center of mass of the C-link to be slightly off-center, because otherwise, and you can try this on your own if you want. If you put the center of mass exactly in the middle, we'll actually get 0 torques needed anywhere, because the system is already balanced without the need for any additional torques. Alrighty, so let's solve this. This is solved. Now this doesn't give us the torques at the joint, so we shift enter. And this piece of code actually calculates the intermediate unknown wrenches and also all the torques, and we see that the torques at the feet are indeed 0 as enforced, and the torques at the hip are actually clockwise. And so this is actually a little bit counterintuitive that we get clockwise torques at the hips, you know, and that they seem to work with the imbalance of gravity. But this system is this actually is the solution for minimizing the torques needed, and the solution is in these negative and positive reaction forces that are created that generate their own torques, and those are cheaper, you know. So this might not be super intuitive. Okay, note that if you put the center of mass in the middle, we can do this. I can easily go back, and then I have to evaluate all the cells where this is used. But I'll put a 0 in here. Now we get a new dictionary. I have to create new screw axes. I have to create a new factor graph, and then solve it. Okay. Inside the body, there is moments, but if we calculate those towards the joints, what you'll see is that the torques in all the joints are 0, because and let's look at the drawing here. Okay, this 4-bar linkage, if the center of mass is right straight in the middle, is just balanced on its own. Now it's an unstable equilibrium. If you just keep on delivering 0 torques, any slight deviation will cause the 4-bar linkage, or the animal, if you want, to fall over, the robot to fall over. So you'd have to do some torque to resist that, right? So you can easily think about, okay, what controller would you need to keep this system stable? But that's not the topic at hand. All right, so going back to, I'm just going to reinstate the off-balance, otherwise everything will be sort of uninteresting. So I'll just put point 1 here again, evaluate all the cells, verify that we get non-zero torques again, and indeed we get our non-zero hip torques again. But what if we wanted to do actuation at the ankles? You know, who's to say that ankles are not more efficient? We need less torque with the ankles. The answer to that will actually depend on the kinematic configuration you choose. In this one, it will turn out not to be the case. But maybe we can have other combinations, like a single joint actuated, all joints actuated, right? So let's see whether we can explore them. And now that we have sort of some code to do the factor graph, we can easily explore all of these. By the way, it started raining here quite violently, so I hope that sound doesn't bother. Okay, how can we explore all actuator designs? Well, I'm going to introduce this objective function, which minimizes all torques, the magnitude of all torques, but with a varying factor sigma, or 1 over sigma here. And it turns out that GTSAM is nice in the sense that if you give a sigma of 0, it will actually enforce a hard constraint, making the torque 0. Otherwise, it will minimize the torque with that weight. We also previously symbolically eliminated the intermediate wrenches and torques, but there is really no need to do the work that GTSAM can do for us. We can create a more complicated factor graph, okay, where we just introduce all unknown wrenches as unknowns, and we introduce all torques as unknown variables. And we now simply say, we're just going to write down all balance equations. We're not going to symbolically eliminate them. GTSAM will do that work for us. And it will also calculate the torques for us automatically just by, in these green factors, saying what the relationship is between torque and a wrench delivered by that joint, which is just multiplication with an axis. So that's, again, a linear equation. And then we can specify our torque minimization objective as a function of these new, if you want, extra unknowns. Yes, we can easily, with some math and some symbolic elimination, get rid of them. But why do all that hard work? This is actually a little bit more representative of what is actually happening. Look at the blue structure here. This is the 4-bar linkage, not counting the stationary link where we don't do a balance. And then at each location, at each joint, we can calculate the torque. So this is an amazing way to look at a 4-bar linkage as a factor graph. And this defines the statics as a factor graph, right? So I'm biased, of course. All right, so let's go on and create a little function here that creates a factor graph for any possible combination of sigmas. So there's these 4 sigmas, and we're just going to use those sigmas in the torque minimization part. Here are the 4 torque definition factors, then we have the body balance and the leg balance, and that's the whole factor graph. And we return that factor graph as the output of this function. And now we can create, whatever factor graph we want. Okay? Note that a factor graph is nothing but a graphical representation of a sparse linear system, right? So if you compare this factor graph here, which has 8 unknowns, okay? You can count them, 1, 2, 3, 4, and then 8. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factors. This corresponds to a sparse linear system where all the unknowns are correspond to columns. Actual columns in the case of the torques, but block columns in the case of the wrenches, each 3 wide. So that's 12 plus 4, right? Which is 18. This matrix is 18 wide. And each factor corresponds to a block row, or a scalar row in the case of these torque factors. But here the balance equations are actually 3 high at every location. And this is a sparse linear equation, a system of equations that is over-constrained, and which we can solve. And that's what GTSAM does. It really is just a factor graph is in fact what we use to represent sparse linear systems inside GTSAM. Okay? But if you want to make a matrix with a lot of zeros, you can go right ahead, and MATLAB has a different representation to store sparse matrices, but a factor graph is just one way to do it. And now we can do this very cute piece of code here where we have a bunch of scenarios, and for every scenario that we give a name, J1 is just a torque at J1, ankles is turn the hips off, hips is turn the ankles off, and all is let all hips and ankles do some work. And then finally, we can actually play with the weights themselves, so I'll explain that last. I'll just run this piece of code, okay? And we have a problem. Create graph is not defined because I didn't evaluate the cell here. So let's do that. Now it should work. Let's do it again. Still not. Tau is not defined. Did I have a missing? Yes, this cell should be. This just creates a little function to create keys for the torques, which are now, before we had a way to create keys for the forces, for the wrenches, but not for the torque, so I needed to do this. Again, evaluating this cell, and right, this was a little bit troublesome, but finally we get there. And so, for example, scenario J1 is just have one torque delivered at the left foot, and you can see that indeed all torques are 0 except 1 Newton meter is delivered at the left foot. Ankles, you can see that ankles, turns of the hip joints, which is 2 and 4, which we had on before, but now the ankles are delivering all the needed torque, and in fact they're larger at the ankles than they were at the hips, right? We can see this immediately by looking at the hip. Let's first look at one joint at the hip. It's 0.5 Newton meters delivered clockwise. And if we actuate both hips, then this 0.5 is simply distributed evenly, because that minimizes sum of least squares to both hip joints, right? It's amazing what we can do, right? With a little bit of code and GTSAM. And then we can do, well, let's have all joints work, and then if they collaborate, all 4 of them, it turns out that the joint torques are going to be smaller than in any of these scenarios above. You might be puzzled why they're not all equal, and that is just a result of the system of linear equations created by the statics. Is that, you know, this is going to be the minimum torque solution. I challenge you to find another one where all torques are similarly punished. That is different. This is truly the global convex minimum. But we can play with the weight. So we can say, let's assume, right, a very reasonable assumption, especially for people and probably also for robots, is that the motors for the hips are probably going to be more powerful than the ankle motors, which have to be maybe in a smaller package or delivered by cables from afar, and so or tendons. So let's make them not do as much work. So adapted here is different from the all scenario, in that we remember that the ankles are T1 and T3, and here we actually make them smaller, okay, by punishing them more heavily, okay. So now more torque is delivered by the hips, favoring the ankles, right? So that's pretty cool, right? So now we have a mechanism to not, you know, so in robotics, and we'll see that in a second, in many cases we have a way to, you know, if some ground reaction forces are needed, we can use something called the Jacobian transpose to deliver these torques. But we can do this in a weighted fashion, so we can use weights to ask the different joints to do less or more work based on what we want. And that is all, again, I'm going to show the factor graph. Okay, I think of this in terms of factor graphs, and it's really about putting these factors or tuning those factors here. And what we did in the adapted case is to say, we're going to just allow these, we're going to allow really what we did is we allow the hips to take up more slack, favoring, by punishing more the torque in the ankles. All right, so this is the end of part B, 25 minutes, 29 minutes. So we will look next at articulated legs. And so if you are interested in what this cute Star Wars dog will do in terms of statics, watch part C.